For decades, we thought Mars died quickly, a flash flood planet where water came and went in geological blinks. But deep in Jezero crater, a robot the size of a car just found something that changes everything. Tiny pebbles. Unremarkable, except for one detail. They could only form under millions of years of heavy rain. The kind of rain that doesn't just carve channels, it builds worlds. Mars didn't die in a drought. It drowned slowly, deliberately, across epochs we're only beginning to understand. And if it had that much time, what else might have grown in those ancient storms? Perseverance wasn't looking for miracles. When it rolled across the western edge of Jezero crater, it was doing what it always does, grinding stone, analyzing dust, mapping the bones of a dead river delta. Then the spectrometers lit up. Kaolinite, a clay mineral so common on Earth, we use it to make porcelain. But on Mars, it's a timestamp. A geological confession written in crystal structure. Kaolinite doesn't form from ice melt. It doesn't precipitate from brief, catastrophic floods. It requires something Mars wasn't supposed to have. Persistence, decades of rain, centuries, millennia stacked on millennia, water seeping through volcanic rock, leaching away everything but aluminum and silicon, building clay deposits grain by grain. The same process that shapes rainforests on Earth shaped this crater on Mars. An alien Amazon, wrapped in rust and silence. Every model we had said Mars lost its atmosphere fast. Solar winds stripped it away. Water evaporated or froze. End of story. But kaolinite whispers a different tale. This wasn't a planet that blinked out. This was a world with weather systems, seasonal cycles, river networks, fed by clouds we never imagined. Somewhere between 3 and 4 billion years ago, Jezero crater wasn't a dust bowl. It was wet. Consistently, reliably, impossibly wet. And wet means something else. Something we've been dancing around since the first Mars. Missions, time, stability. The two ingredients life needs most. Not just water for a few thousand years, but stable climatic conditions across millions. Long enough for chemistry to experiment. Long enough for complexity to emerge. Long enough for something to take root in the mud of an ancient delta and leave traces we're only now learning to recognize. The implications cascade outward like ripples in one of those vanished lakes. If Mars maintained a thick atmosphere and active hydrological cycle for that long, then the window for potential life wasn't a crack, it was wide open. And if life found a way to start, it had epochs to adapt, to spread, to dig in before the planet turned hostile. While Perseverance studied the past in pebbles, orbiters circling overhead were hunting for the future. And they found it, not in the rocks, but in the absences between them. Skylights, circular voids punch through ancient lava flows, dropping into darkness we can measure but not see. Some are the size of tennis courts. Others could swallow buildings. They're not craters, they're portals. Radar scans suggest these aren't just holes. They're entrances to vast cave networks carved by lava tubes when Mars still had active volcanoes. Tunnels stretching for kilometers, shielded by meters of rock. And that matters because Mars has no magnetic field, no thick atmosphere. Nothing to stop cosmic radiation from sterilizing the surface. Above ground, organic molecules break down in years. Below, they could last billions. If life ever emerged in those ancient rivers, it would have fled underground when the rain stopped. Down where ice might still exist, down where radiation can't reach, down where biosignatures, chemical fingerprints of metabolism, fossilized microbes, maybe even dormant spores, could wait in the dark, untouched, perfect. We've been searching for life on a surface scoured clean by time and radiation. The real archive might be beneath our feet, preserved in chambers that have been sealed for 3 billion years. Think about what that means. Every rover we've sent has been scratching at the surface, drilling centimeters into bedrock, analyzing dust that's been bombarded by cosmic rays for eons. But these caves are time capsules, protected environments where the chemical signatures of ancient biology could remain intact, waiting for the right instruments, the right questions, the right explorers willing to descend into the Martian underworld. And when astronauts finally reach Mars, they won't set up camp in the open. They'll descend. These caves aren't just scientific targets. They're the first Martian shelters. Natural habitats with stable temperatures, radiation shielding, and possibly water ice locked in the walls. The first Martian base won't be built from prefabricated modules trucked across the surface. It'll be discovered, explored, and occupied. Humanity's first steps toward becoming an interplanetary species might lead downward into the very spaces where Martian life, if it ever existed, might have made its last stand. In the northern reaches of the crater, Perseverance found a rock that shouldn't exist. Not because of what it's made of, sedimentary layers aren't unusual, but because of what's inside it. Leopard spots, hundreds of them, millimeter-scale rings of black and white minerals, arrayed in patterns so regular they look designed. The rock has a name now, Cheyava Falls, and it's become the most scrutinized stone in the solar system. Each spot centers on a dark core, rich in iron and phosphate. Each is surrounded by a halo of calcium sulfate. On Earth, only one thing makes patterns like that consistently: life. When microbes consume energy, they create chemical gradients. Waste products migrate outward from the colony, precipitating minerals in concentric rings. It's how stromatolites form in shallow seas. It's how bacterial mats leave fossils in ancient lakes. And it's exactly what these spots look like: chemical bullseyes marking where something might have fed, metabolized, and died billions of years ago. The iron and phosphate, exactly what primitive cells use for energy transfer. The calcium sulfate, a burial shroud, preserving what came before in mineral form. But here's the tension that keeps scientists awake at night. Geology can mimic biology. Mineral precipitation can create patterns that fool even expert eyes. Temperature gradients, chemical diffusion, crystallization fronts. All can leave marks that resemble the fingerprints of life. The team knows this. They've run every non-biological scenario they can imagine. Some fit parts of the puzzle. None fit perfectly, which leaves us in the most tantalizing position science offers: genuine uncertainty, backed by compelling evidence. The spots are too small for Perseverance's instruments to definitively analyze. We need those samples back on Earth. We need laboratory analysis with instruments that can detect individual organic molecules. We need isotope ratios that could distinguish biological from geological carbon. We need to see if there are structures with cell-like boundaries, if there are patterns that pure chemistry alone cannot explain. Cheyava Falls isn't proof of ancient Martian life, but it's the strongest candidate we've ever found. A rock that whispers possibilities we've been chasing since the first telescopes turned toward the red planet. And it's sitting in a crater that once hosted millions of years of rainfall, surrounded by cave systems that could harbor even better preserved specimens. These discoveries are rewriting the mission brief for everything we send to Mars next. The sample return campaign has transformed from a geological survey into a biological treasure hunt. Those kaolinite pebbles, the Cheyava Falls rock, samples from near the skylights, they're coming home. And when they arrive, they'll face the most intensive analysis ever applied to extraterrestrial material. But robots have limits. The caves demand human exploration. The deep stratigraphy needs drilling beyond rover capabilities. Within 2 decades, astronauts will stand in Jezero Crater with one mandate: find out if we're alone. They'll rappel into skylights. They'll core drill through ancient clay beds. They'll search for biomolecules our current instruments can't detect. Because if Mars had life, even briefly, it means life isn't a cosmic accident. It means chemistry tilts toward biology when given water and time. It means every world with ancient rivers might have had its chance. Perseverance keeps rolling, grinding stone, analyzing dust. It doesn't know it's rewriting our understanding of planetary evolution. It just follows its programming under alien skies. But we know what those pebbles mean. We know what those caves promise. We know what those leopard spots might be screaming across eons of silence. Mars remembered its rain, locked it in clay, hid its secrets underground, left us breadcrumbs written in minerals and preserved in darkness. And we're finally learning to read the message.